Welcome everyone. My name is Aishwaryo ghosh, GRF first year at the Department of CMPMS, working in Professor Tanushree Shah Dasgupta's group. Title of my talk today will be Machine Learning in Material Science. A machine learning algorithm implemented in a computer program can learn about patterns in high-dimensional empirical data made available to it by modeling linear or nonlinear relationships among them. And it can do so without direct human interference or assistant. So it sort of imitates how humans learn and gradually improves its accuracy. With exponential increase in computational efficiency and availability of data, machine learning can be incorporated into research to assist discovery of novel materials with important properties. Since the huge compositional space assures large number of undiscovered materials, machine learning can hugely benefit the conventional ways of experimentation and simulation. It can also predict microscopic and macroscopic properties, find density functionals, force field, etc. Machine learning algorithms can broadly be divided into supervised learning and unsupervised learning. Supervised learning is characterized by its use of labeled datasets. These datasets are designed to train or supervise algorithms to classify or predict outcomes accurately. It again has two subcategories. One is classification, where data used have specific categories, like separating apples and oranges. Some examples of such algorithm are decision trees, support vector machines, and random forest. The other is regression, that helps in predicting numerical values by establishing a relationship between independent and dependent variables. Some examples are linear regression, polynomial regression, and so on. Another broad division is unsupervised learning, that analyze and group unlabeled data. It again has two major subcategories: clustering and association. Next, we'll be discussing the workflow of a machine learning algorithm, which has 4 stages, and we'll be discussing them one by one. The first step is dataset construction. A learning dataset has two parts. It has instances, or each separate entry in the dataset. These are the rows. And then we have attributes, which tabulate information about each instances. These are the columns. And they are generally microscopic or macroscopic physical and chemical properties of the instances. Their data are gathered from literature, maybe some online databases, and for some cases, some high throughput calculation can also be required. In pre-processing, generally missing data are removed. Then the data might be normalized or standardized as is needed by some algorithms. Then data imbalances, where data points belonging to one class are more than other, those are managed. And finally, relevant attributes are chosen. Next, the model is built and efficiency of the model is evaluated. The evaluation is done such that the model is always evaluated on data unseen by it during the training. And for this, techniques like cross-validation or trend test split are used. In case of regression, error matrices like mean absolute error, mean absolute percentage error, RMSE, all these are used. And in case of classification, error matrices like accuracy, confusion matrix, precision, F-score, all these are used. And after we have built the model, it is saved, and then prediction on some unseen data using that model can be made. So let's come to example 1. This work has been published in Peer Applied. The aim of work is to search for efficient rare earth transition metal permanent magnets employing machine learning and first principle approach. The transition metal in these magnets contribute to high saturation magnetization as well as high Tc, and the rare earth contributes to strong magnetocrystalline anisotropy owing to the spin orbit coupling. Now we know about SMCO5 and NdFe14b are two prominent commercial rare earth transition metal permanent magnets. However, keeping in mind resource criticality of rare earth elements like samarium and neodymium, finding rare earth lean intermetallics using abundant rare earth elements can be helpful. Coming to the machine learning part, there are several types of RETM compounds to be explored, like binary compounds, among which RM12, RTM17, and RTM14 compounds can be examples of rare earth lean compounds. We can also have interstitials like boron, carbon, and nitrogen inserted. Our learning set are formed of these instances as found in experimental literature. For attributes, we have chosen stoichiometric, elemental, and electronic properties of the constituents as can be seen in this chart. A good permanent magnet should have a Curie temperature high enough, like 600 Kelvin, high saturation magnetization with mu-0 values of at least around 1 Tesla, and a mechanism for creating sufficiently high easy axis anisotropy, which is given by Ku. So to implement this, we create a database of TC, MS, and KU, and use machine learning for prediction of TC values via regression, and estimating whether mu-0 is larger than 1 Tesla, and predicting the sign of KU. The last two are classification problems and serve the purpose of initial screening. And we have tried out several machine learning algorithms and found that random forest is best for this purpose. we choose this class of compounds as the exploration set for application of our trained machine learning algorithm. And the reason behind such choice is that cerium is the cheapest rare earth. Also, that 2:17 family is majorly sampled in our model, and it is stabler than 2:14 family. Then iron, which is cheaper than cobalt, it has large saturation magnetization. And then experimental findings support that nitrogenation and carbonation can switch the anisotropy from easy blend to easy axis in iron rich compounds, and also that carbon and nitrogen interstitials can help increase TC. Our ML predicts that the nitrides and carbides increase TC with respect to their parent compounds, and that nitrides have higher TC than carbides. We also note that the trend in increase of TC in interstitial compounds as compared to parent compounds. So when X varies from 0 to 8, such increase varies from around 200 Kelvin to 10 Kelvin for carbides and nitrates, and 310 Kelvin to 30 Kelvin for presence of both nitrogen and carbon. This repository this actually reproduce the experimental data in a qualitative manner. For classification in MS, all compounds are classified in favor of forming permanent magnet as mu naught MS is greater than 1 Tesla. For compounds like Ce2Fe17-X COX, the prediction confidence for such lies between 0.6 to 0.8, while for the carbonated and nitrogenated compounds, this classification is always done with high prediction confidence. For KU classification, we see that anisotropy for Fe17-X COX compounds, they are easy plane, while the carbonated, nitrogenated or carbonitrogenated ones are easy axis. We also see that pure iron compound except the carbonitrogenated one, they are easy plane. And we also see that Fe16CO with presence of carbon or both carbon and nitrogen, they are easy axis. And in all the cases, prediction confidence are nearly 75%. On the basis of the above machine learning analysis, we pick up 7 yet to be synthesized compounds of this class and do detailed calculation on it. We see that the total magnetic moment decreases with increasing cobalt concentration as cobalt moment is less than iron. However, the highest cobalt concentrated compound, that is Ce2Fe10 CO7CN, it has mu naught ms value of 1.65 Tesla, which is an agreement to the ML prediction of it being greater than 1 Tesla. We also find that all MA, they are positive in agreement with our machine learning prediction, and the values show non-monotonic dependence on cobalt concentration. We also calculated some technologically interesting figures of merit like maximal energy product BH, which ranges from 442 to 538 kilojoule per meter cube, and anisotropy field with strong variation with cobalt concentration and varies from 1 Tesla to 14 Tesla. Let's move to example 2. Heterojunctions, formed as an interface of two dissimilar semiconductors, is one central topic in semiconductor research. In this study, we attempt database-driven and machine learning-assisted prediction of types of binary semiconductor heterostructures. Heterostructures can be classified as type 1 or type 2, depending on sign of the band edge discontinuities. In type 1, valence band and conduction band offsets are opposite signs, so both conduction and valence band edges of smaller bandgap semiconductor lies within the bandgap of the other. In type 2, offsets are same sign and a staggered alignment of band edges occur. In the present study, we use existing digitally accessible electronic structure database to calculate branch point energy, then apply scissor shift to it and use it as a measure of common absolute energy level for band alignment. We then verify its prediction with experimental values of valence band offset and conduction band offsets with high correlation. And finally, we predict the types for all possible heterostructures. Let's move to the ML part. Since prediction of type can be made out of individual band structure information, the features that are considered here are of individual semiconductors. These are the attributes or features that has been considered. We start with 12 into 4 attributes as each semiconductor contribute 2 elements. The 2 additional features of GGA band gaps of the semiconductors are taken. Since the dataset was small, we used a synthetic data generation technique to expand it to 78, and which are built on an image of the original data actually. So then using a Aishwaryo regression model for sets, we get reasonable errors to validate our algorithm. Next, we transform the problem to a classification one where only sign of the offsets determine type 1 or type 2. For this, to get a better result, we converted the 50-dimensional set to a set of 2, 3, 4 to 5 features using third order polynomial combination of the features. The classification model thus built predicted 86% of the cases correctly. Finally, based on the model, we predicted all possible heterostructure combinations and matched with previous band alignment results, and thereby we found 88% matching with it. To further validate our ML algorithm, we actually did first principle calculation on two heterostructures. One is ALP-GAP and the other is ZNO-GNN, and the type that we got from this detailed calculation matched with the type prediction from our ML algorithm. Finally, we tried to apply this both band alignment and ML approach to heterostructured nanoscale. To do that, we added a quantum confinement correction given by the Brush equation here, R being the radius of nanocrystal. And even at such approximation, we were able to reproduce the experimental trend of size-dependent CBU and VBA between ZNAC and CDS quantum dot. For the ML part, with the existing 31 cases, we added 5 other nano heterostructure cases and also added 2 features for quantum confinement terms for the 2 semiconductors. Then we followed the previous workflow. This time it correctly predicted 82% of the cases in training set. So we have seen that machine learning has a huge prospectus in study of material sciences. With new data being added at repositories every day, the field of machine learning assisted research is certain to give us more interesting results in the future. Thank you.